Let's take a look at another example of macroscopic description of ideal gases. A sturdy balloon with a volume of 1/2 cubic meters is attached to a 2.5 by 10 to the 10 squared kilogram iron weight and tossed overboard into a freshwater lake. The balloon is made of a light material of negligible mass and elasticity, though it can be compressed. The air in the balloon is initially at atmospheric pressure. The system fails to sink and there are no more weights, so a skin diver decides to drag it deep enough so that the balloon will remain submerged. They want us to find the balloon at the point where the system will remain submerged in equilibrium. So they're looking to get to some depth where we can compress that balloon. So as the balloon and the weight are dragged deeper into the lake, the air in the balloon is compressed and the volume is reduced along with the buoyancy. At some depth, h, the total buoyant force acting on the balloon weight, B balance plus B Fe, will equal the total weight. The weight balance, the weight Fe, and the balloon will remain at that depth. Substitute these forces into Newton's second law and solve for the unknown volume of the balloon. Okay, so we're going to find the volume of the balloon at the equilibrium point. So this is the point we're trying to find, the volume of the iron. Okay, Fe is the symbol for iron. V sub Fe. So V sub Fe is equal to the mass of the iron divided by its density. So you'd have to look up the density. 2.5 times 10 squared kilograms, 7.86 times 10 to the third kilograms per meter cubed, gives us a volume of 0.0318 meters cubed. Okay, so now we've got that volume. Find the mass of the balloon then, which is equal to the mass of the water if we neglect the mass of the balloon's material. So we have the mass of the balloon then that we're trying to solve for is equal to the density of air times the volume of the balloon, so rho v. So 1.29 kilogram per meter cubed times 1/2 meters cubed gives us 0.65 kilograms for the mass of the balloon. Apply Newton's second law then to the system when it's in equilibrium. So we end up with B sub Fe minus W sub Fe plus B of the balloon minus the weight of the balloon equals 0. Okay, so that's in equilibrium. Substitute the appropriate expression for each term. So the density of the water times the volume of the iron times the acceleration of gravity minus the mass of the iron times the acceleration of gravity plus the density of water, the volume of the balloon, the acceleration of gravity, minus the mass of the balloon times the acceleration of gravity equals 0. So we can take out all of the acceleration of gravity terms because they're constant throughout and solve for the balloon's volume, V sub BAL. So the mass of the balloon plus the mass of the iron weight minus the density of the water times the volume of the iron weight divided by rho water, the density of the water. So we enter all of those terms into our expression here below, and we end up with the volume of the balloon is equal to 0.219 cubic meters of volume. Next part of the problem asks, what's the balloon's pressure at the equilibrium point? Okay, so the point where the diver has pulled the balloon and the weight down to a point where it doesn't try to go up anymore because the air has been compressed. Use the ideal gas law to find that pressure, assuming the constant temperature, so that T initial equals T final. So we're making that assumption that the pressure is constant, and we're going to use the ideal gas law, PV nRT. So since we called the temperature constant in the PV-nRT relationship, all of those terms cancel out and we're equal to the final pressure, final volume, initial pressure, initial volume set equal to 1. Okay, so that's the equilibrium point. So in doing this, then we can separate our terms, final, final, initial, initial, rearranging our terms for pressure final equals the volume initial over volume final by pressure initial. Insert our terms, half a cubic meter, 0.219 cubic meters times the atmospheric pressure, 1.01 times 10 to the 5th Pascal, and we end up with a final pressure where the balloon is at equilibrium of 2.31 times 10 to the 5th Pascal. Part C asks us then, to what minimum depth must the balloon be dragged? So we use the equation of hydrostatic equilibrium to find this depth. So the final pressure is equal to the atmospheric pressure times rho GH. We can solve then for H from this relationship by moving our terms around so that we have the depth, in this case H is equal to pressure final minus the atmospheric pressure divided by the density and the acceleration of gravity, rho G. So we insert our terms in here, take the difference in the final and the atmospheric pressure, take the product then of the density in water and the acceleration of gravity, and we end up with the height, or the depth in this case, where the balloon must be dragged for it to be in equilibrium, as 13.3 meters of depth. The ideal gas law then was used in this problem then to good effect. The problem shows how even answering a fairly simple question can require the application of several different physical concepts: density, buoyancy, and the ideal gas law, and hydrostatic equilibrium. So the next section here covers something called the kinetic theory of gases. So we're back to our kinetic relationships and those models.